Go ahead with introduction. So welcome everybody to the seminar of the Australian Centre of Excellence in Antarctic Science. Today, our speaker is Taimoor Sohail. Sorry, Taimoor. Taimoor is a postdoctoral researcher at UNSW in the School of Mathematics and Statistics with Jan Zika and John Church. So Taimoor is currently an associate investigator with ACEAS, but from January or April? April. Oh, it's Jan. So from April, he will be an ACEAS postdoc, which we are very grateful for. Taimoor received his PhD from the Climate and Fluid Physics group at ANU in 2020. His research interests include studying the processes which drive ocean heat and freshwater changes, ocean ventilation, and large-scale circulation, both globally and in the Southern Ocean. So he likes to study the role of convection and turbulence in driving mixing, as well as the broader role of ocean mixing and surface fluxes in driving large-scale ocean changes. So today, I think he'll present us the results of work that has been published recently, I think, which was very nice paper. So thank you, Taimoor, and I'll leave it to you to show us your work.
Great. Thank you, Laurie. Yes, so as Laurie said, I'm not going to be presenting specifically on Antarctic things today, but I will give you a sneak peek for what my plans are once I start with ACEAS next year. Today, I'll be talking about work that I've been doing on the global ocean and how the heat and freshwater content changes in the global ocean, specifically looking at things through a water mass-based lens. And yes, this is work I've done with Jan Zika, John Church from UNSW, but also Ryan Holmes from University of Sydney and Damien Irving from CSIRO in Tasmania. Okay. So I'll start with sort of the bare bones basics of why we sort of pursued this research question. We were really interested in how the impact of the global ocean on modulating climate change over time in our sort of past since the 1970s. And the reason we were interested in this is because the global ocean is very important in hosting a huge proportion of excess heat that builds in the climate system. And it also actually acts as a conduit for the fresh water that exists in the water cycle. So a lot of that fresh water transits through the ocean on its way to raining in the land or in other parts of the world. So the most recent estimates suggest that about 89–90% of the excess warming or radiative forcing that builds up in the climate system is actually absorbed by the ocean. And a growing proportion of that is absorbed by the deep ocean, which is this, I hope you can see my cursor, but this is the dark blue section over here. And so this is an IPCC estimate of the heat that's been stored in the ocean since 1970 to 2013. Not only that, but as I said, 80% of the water cycle transits through the ocean. And one of the sort of wrinkles in this process is that we can't directly measure the rates of evaporation and precipitation over the ocean. It's just not really feasible to have fixed rain gauges or evaporation pans floating on the ocean surface. And so measurements of the water cycle as it transits through the ocean are quite scarce. So one way that we can track changes in ocean heat content and freshwater content is by tracking ocean temperature and salinity. I'll talk a little bit more about the salinity aspect of things, but specifically with ocean temperature, the warmer the ocean is getting, the more heat it's absorbing from the overall climate system. But there are a few problems here. First of all, our level of observations, density of observations over time, particularly for salinity, have been growing, but are still quite lacking. So on the left here, you have a split of the density of temperature observations in the northern and southern hemispheres. So it's colored by global coverage. And you can see that while subsurface temperature up to 500 meters has been pretty well observed since the 70s, We're only now starting to get down to 2,000 meters since the advent of the Argo program. And this is a much more acute problem in the Southern Hemisphere, predominantly due to lack of observations in the Southern Ocean. Salinity is definitely even worse. Historically, we have about a third of the salinity measurements that we do temperature. With the advent of the Argo program, I apologize, the years have been cut off, but this is around 2000. With the advent of the Argo program, we've gotten a much greater coverage of salinity, but this is all down to 2,000 meters. So the deep ocean, what's happening in the abyss? Oh, sorry. What's happening in the abyss is not as obvious. The other thing is that if we want to track, for example, ocean heat content change in CMIP6 models, it is actually highly variable. So on the left, I'm plotting the global ocean heat content since 1870 in the CMIP6 models. These are 30 different CMIP6 models in light gray and the CMIP6 mean in dark gray. And I've overlaid that with an observational estimate, obviously gets highly uncertain pre-1970, but this is based on the Lorzana 2018 paper. And so you'll notice a few things. The first is that CMIP6 models in general underestimate the buildup of ocean heat since the 1870s. But secondly, the spread between different CMIP6 models is extremely large, with some models showing essentially very little increase in ocean heat content and others showing an extremely high increase in the ocean heat content. That's all, by the way, with a backdrop of the heating of the surface that is quite tightly constrained. So there's not a lot of variability there. So, so given the amount of variability in the models and also uncertainty in the observations, a lot of work has gone into moving to a water mass space. Essentially, what it means to look at changes to the ocean in water mass space, it means to track changes to ocean properties along and across surfaces, isosurfaces of constant tracer. So whether that's along and across temperature surfaces or isotherms or isohalines, so salinity surfaces, or isopycnals, which is density surfaces. Basically, using water mass space, we can track changes to the ocean along and across these surfaces. And this presents an alternative to a more Eulerian way of looking at things, where when I say an Eulerian way of looking at things, I mean fluxes across latitude or longitude bands or across different depth levels. Here we're looking across surfaces of constant tracer. So one very commonly used water mass framework is looking at things in TS space. So here I have a plot of the volume of the ocean in temperature and salinity space. So you can see a huge proportion of the ocean. This is from observations, EN4. You can see a huge proportion of the ocean has very high volume, has a very narrow range of temperatures and salinities, which is over here. And then we see a large spread which includes the surface ocean and other places that have highly variable temperatures and salinities. So there's a few benefits of why we would move into water mass space to assess ocean heat content and freshwater content. First of all, TS space is sort of a natural means of visualizing different ocean water masses. So on the right here, we have a plot from Gerskamp et al. Where he basically colored the sea surface with different colors and then just plotted those colors based on the sea surface temperature and sea surface salinity. And what you can see is that the Southern Ocean, for example, occupies a characteristic space in TS. The Arctic is this long, skinny thing at the bottom. And then we have the tropics up here, which are constantly mixing with one another, the tropical Indo-Pacific and tropical Atlantic. And then we have some marginal seas that present outliers, particularly in salinity space, because the Mediterranean, Red Sea, and Persian Gulf are quite salty compared to the global ocean. More broadly, we can split the ocean into climatic zones. So we say, the tropics are defined by some temperature bound, the subtropics defined by a different one, and then the subpolar and polar regions defined by some other bound. So we can easily visualize changes in TNS in TS space. So as these volumes dance around, what you're predominantly seeing here is the seasonal signal as we move through the months. But you can see that there's a lot of mixing and interleaving between different water masses in the tropics and surface ocean, whereas the deep ocean tends to stay relatively fixed over time because the seasonal cycle isn't reaching the deep ocean. Or the deep ocean will show us a more long-term change in the characteristic TNS of the ocean. So the changes in TS space are only due to diahaline or diathermal fluxes. That's just what happens when you transform into this space. Any change in the volume has to occur along the horizontal or along the vertical. So basically across isotherms or across isohalines. So this naturally excludes these adiabatic fluxes, which can rearrange water parcels, but don't actually sort of mix as they do that rearrangement. So for example, if we just take a cold and hot water parcel and we just swap their location, in Eulerian space, or in lat long depth space, we would see that as a change in the heat content or the salt content. But in TS space, nothing has actually happened. There's still the same volume with the same characteristic TNS, so it won't show up in TS space. And finally, in a closed system, so looking at the global ocean, the heat and salt budgets are going to be simple combinations of surface fluxes and mixing. So whatever goes in at the surface affects the heat content or the volume of the isosurface. And the only way that things can leave that patch or that water mass is via dia surface fluxes. So this is from Holmes et al. 2019. So hopefully I've convinced you that water mass theory is a good way of trying to quantify ocean heat and freshwater fluxes. So the aim of the work that I'll be presenting was to try and understand the global heat and freshwater budget using a water mass transformation framework applied to models and observations. And there's three key ingredients here. We take some volumetric data, whether that's observations, models, what have you. We apply a water mass transformation framework to it, and then we obtain a heat and a freshwater budget. And you'll see that this is a methodology we pursue for a lot of the work that we do. So the first question is, what is the water mass transformation framework that we're interested in? Well, I just presented to you TS space or T space, but we look at things slightly differently. So we'll go back to the climatic zones I was talking about. We can partition the ocean based on its characteristic temperature into these zones, but in a warming ocean, suddenly we're not really sure where the tropics lie or where the subtropics lie based on the characteristic temperature, because of course the whole ocean is warming. So what was maybe 25 degrees in the past might actually be 30 degrees in the future. This is particularly acute for strongly forced ocean models or for SSP scenarios, so future projections of the warming ocean. We call this a regime shift. So essentially, if we're looking at sort of a one-dimensional framework, we have these volumes bounded by a fixed isotherm, right, θ3. And as the ocean warms, assuming it sort of warms uniformly, that θ3 will move northwards, or towards high latitudes, I should say. And what that means is that you'll end up occupying a much greater volume, and it'll be outcropping maybe in the new subpolar or subtropics region rather than in the tropics. So what we do is, it's a very sort of simple change in the conception, but instead of tracking changes at fixed temperatures, or indeed fixed salinity, we track changes at fixed temperature percentiles. What that means is we're basically, instead of tracking changes at, let's say 14 degrees Celsius, so you can think of that as a bowl of water that's 14 degrees Celsius or warmer, we track changes in the X% warmest ocean. So basically, we'll be tracking changes in the 10% warmest ocean by volume. The 10% warmest ocean by volume will, by construction, always have the same volume, even as the ocean warms. It'll just have a higher characteristic temperature as the ocean warms. And this is a slight change in the frame, but by moving to sort of a fixed volume framework, so 10% warmest ocean rather than 14 degrees Celsius isotherm, We can do cleaner intermodal intercomparisons because different models will have different, like some will be warmer in general and some will be colder in general. So if we fix the 10% warmest, we've got a cleaner slate to compare between models and observations. We can compare with Eulerian frameworks, which is latitude, longitude, and depth. Those are fixed grid cells. They have a fixed volume as well. So we can compare more easily between water mass and Eulerian frameworks. And finally, we can actually formulate a simpler heat budget, which I will discuss later. So the other thing I just wanted to say is that we can also define percentiles in 2D space. So what I showed you here was sort of a one-dimensional framework. We're just looking at the 10% warmest ocean. But we can also track the X% warmest, saltiest, or coldest, freshest ocean. So in a 2D space. I'm not going to go into this in this talk because I'm sure I've already confused you enough. But just briefly, if you're interested, what we do is we take the TS distribution of the ocean. You saw this before. And we basically define bins such that each bin, defined in this red over here, contains 1/256 of the total volume. That can obviously be tuned. We can change that to however many bins we want. These bins shift dynamically so that they always incorporate the same volume of the ocean. And essentially what we're looking at here is two-dimensional percentiles. So the X percentile, warmest or coldest, saltiest or freshest water mass in the ocean. So I'm not going to move into 2D space for this talk. I will talk about it a little bit more at the end, but we'll stick to our 1D temperature percentile framework. So now what we're going to do is we're going to put in some volumetric data, apply our 1D temperature percentile framework, and get some heat and freshwater budgets out. So let's first look at the ocean heat content change. So a fair amount of work has gone into understanding how the ocean heat content changes in temperature space. So if we have those isotherms, for example, that 14 degrees Celsius isotherm, how does the heat content bounded in the volume bounded by that isotherm change? So Ryan Holmes at University of Sydney formulated a heat content in temperature space, which was essentially the theta dV, so the volumetric integral of temperature above a given isotherm theta star gives us the heat content. So like I said before, changes in heat content in this framework will be only due to diathermal fluxes, that is mixing and surface fluxes, and any adiabatic redistributive processes will be excluded. So in theory, we'll have less noise as well due to advection that is adiabatic. Now, in percentile space, we have a very similar heat budget. We calculate the heat content bounded by a given percentile or percentage of the ocean volume. And it's essentially the same thing. So we just integrate temperature of a given percentile by the volume held by that percentile. And I guess what's important to point out here is that the heat content change in a given percentile bowl will be proportional to the surface fluxes that go into the ocean and the mixing between different percentile surfaces. I'll show this to you diagrammatically later. But the other thing that's kind of cool about the ocean heat content change is that it is volume invariant, because we're basically saying it's the 10% warmest ocean. Assuming the total ocean volume doesn't change much, it's going to be proportional to the temperature of that bowl. That's not as important here, but I just wanted to point it out. So diagrammatically, if we go back to our sort of idealized temperature percentiles in the ocean, what we're essentially saying is the change in heat content in a given layer is going to be only due to surface fluxes that go into that layer or out of that layer, and mixing between that layer and adjacent layers. So what we do is we drop in some gridded observations, hydrographic observations and climate models, apply this temperature percentile framework that I've just introduced, and we calculate heat and freshwater budgets through that. The observations we use for this part of the work is a temperature data set it's 1 degree by 1 degree. It's been gridded with 53 vertical levels. So it's important to remember that some regions of the ocean that are more poorly observed, that uncertainty will carry through into this method because these have been gridded, and the way that they infill gaps is different. But for EN4, they infill based on the climatology. For IAP, they infill these gaps based on a CMIP5 model. So you just have to remember that there's still a lot of uncertainty baked into using these observational data sets. And we also use 30 CMIP6 models. So these are historical runs from 1850 to 2014, and they've been de-drifted from the pre-industrial control. And we analyze the period of 1970 to 2014, where the most sort of acute heat content change has been occurring. So we'll just jump into the results. We find some very interesting results. So the first thing that we see, and what's plotted over here, is the heat content tendency in temperature percentile space. So this is slightly different to temperature space. And we've integrated it from hot to cold. So it's actually the slope of these lines that show you how much the heat content is actually changing within each layer, because this is an integrated quantity. Some water. Now, because it's an integrated quantity, at 100%, the values that you see here in these light gray lines are exactly the same values as you saw in my motivation slide. So that's the total ocean heat content of the CMIP6 models, and you can see how highly variable it is. And the CMIP6 mean is slightly less than observations, just as I showed you before. But what it also shows you is that there are some characteristic layers where there is an increase in ocean heat content tendency, such as in the warmest layers, where there's quite a high slope. The flatter the slope, the more heat content basically is being taken up by those layers. It's a bit complicated, but so yes, we have a fair amount of heat being absorbed here, and that amount of heat being absorbed decreases as we go towards the colder and deeper parts of the ocean because it's been integrated. So if you remember, I formulated a heat budget that basically said the heat content tendency is a function of surface fluxes and mixing. So we can also look at the surface fluxes in temperature percentile space. And we don't have a reliable observational estimate of surface fluxes in surface flux tendencies, I should say. So we just look at the CMIP6 models, which again have a fair degree of variability between them. But you can see that there's different regions in which the ocean is taking up heat. There's a little region where there's a decrease in how much surface heat is being taken up, but for the most part, the ocean is absorbing heat at the surface. And finally, the residual by construction needs to be the mixing in the ocean. And so we see that there's a fair amount of mixing in the surface ocean. It sort of dies down, and then there's also a fair amount of mixing in the cold parts of the ocean, basically the high latitudes. So we don't have estimates of surface fluxes or mixing for observations, obviously, because reanalysis products are not particularly reliable when it comes to tendencies. But what we can do is we can look at the ratio between surface fluxes and heat content tendency. So basically, how does the heat content tendency relate to surface fluxes in CMIP6 models? And so we get a linear regression with an uncertainty associated with it. And now all we need to do is we just multiply this black line by this linear regression, and we get an estimate of surface fluxes, and then we subtract the two to get an estimate of mixing. And so that's what it looks like. This is an observationally constrained estimate of surface fluxes and mixing tendencies in the global ocean in this percentile space. So we have our different percentile layers, and this is sort of how much the heat content changes. And that's just based on this black line over here. But we can also infer the mixing and the surface fluxes in the same way I told you before, using this linear regression over here. And what we find is that a huge proportion of the surface flux tendency basically is absorbed at layers that have a very small outcrop area. These are all drawn to scale, so the horizontal length is the outcrop area. So you can see these huge surface flux tendencies occurring in about 25% of the ocean surface area. And these surface fluxes, it basically implies that the representation of surface fluxes and the representation of the ocean in these, this 25% of the ocean is going to be very important for about 90% of the heat content tendency that occurs there. And by the way, this part of the ocean is essentially your subpolar region, so the high and the northern and southern hemisphere high latitudes. Okay, so we've been able to sort of infer this nice budget and tendencies for observations. So let's see if we can turn our attention now to freshwater content change. We've looked at temperature changes. Now, basically, let's look at salinity changes. And so I mentioned at the top that 80% of the freshwater cycle transits through the ocean. As it transits through the ocean, it actually leaves a signature on ocean salinity. So where there's net evaporation at the ocean surface, you end up with a bowl of salty water. And where there's net precipitation, you end up with a bowl of fresh water. So what we can do is, instead of directly measuring the atmospheric evaporation or precipitation, we just measure how the salinity in the ocean changes. And that can be a good dynamic rain gauge, essentially, for what's going on. So let's start by looking in latitude, longitude, so Eulerian space. And what we're showing here is the zonally average salinity tendency in these plots over here for observations in this column and CMIP6 models in the right column. On top, this line plot shows us the surface fluxes that are imposed on average as a function of latitude. And these are also from ERA 5 reanalyses and also from CMIP6 models. So what you can see immediately is that that signature on salinity from surface freshwater fluxes is quite obvious. Where you have a net evaporation, which is these red zones, you have a net salinification of the ocean. Where you have precipitation, it's really hard to see, but there is some precipitation as well. But it is highly variable based on the ocean basin of interest. So the Atlantic tends to be a lot saltier than the Indo-Pacific. And also that signature of salinification tends to build up in the Atlantic. CMIP6 models show a similar trend, but there are some marked differences between the observations and CMIP6 models, specifically this sort of bowl of freshening that occurs over here that's absent in the observations. But also you don't have this uniform band of salinification that you do in observations of the subtropics. That doesn't really exist in CMIP6 models. The stippling shows where the models agree. And the contour lines over here are basically an illustration of the zonally average temperature percentile surfaces. So it gives you a good sense of where these different temperature percentiles outcrop and where they exist in the ocean. So there's a fair bit of variability between these. So let's try and understand this in water mass space again. So what we do is we take the ocean's volumetric TS distribution as before, and we calculate a mean salinity. So we just take an average at each temperature to get this sort of characteristic question mark curve. And we can call this the mean salinity of the ocean. We apply this tracer percentile framework again to observations in CMIP6 models. In this case, we're using an additional observational data set because we wanted a range just to understand what the uncertainty is. So we're also looking at Ishii et al. And we take 20 CMIP6 models plus 6 DAMIP models. I won't discuss the DAMIP results here, but they are in the paper if you're interested. DAMIP is basically simulations where the climate is forced with just greenhouse gases or just anthropogenic aerosols. And it gives us a broader range of responses than if we just had the historical, which is sort of a combination of the two, such that it's closer to the control. These are, once again, historical runs, so from 1850 to 2014, and we look at the period 1970 to 2014. So what are the results? So the first thing I'll just say is in the observations, which are on the left here, and the models, which are on the right, we get the same type of characteristic question mark curve for the mean salinity in the ocean. So that's this dashed line over here. Generally, the tropics are fresher, subtropics are saltier, and then we have a fresher subpolar region. Same is true for the CMIP6 models, but what I've plotted in these arrows is the trend between 1970 to 2014 times 100. So basically, if the 1970 to 2014 linear trend existed for a century, this is how the TS curve would change. So one thing you can see is that a lot of the subtropics are salinifying in the observations. This left panel is the observations. We have a bit of freshening in the tropics, and we have some freshening in the subpolar oceans. So this is actually following established literature in the field, which basically suggests that wet regions of the world are going to get wetter and dry regions of the world are going to get drier. So basically the contrast in salinity is going to increase. And that's what you see. You see this curve getting sort of curvier as salty regions get saltier and fresher regions get fresher. The same is true for CMIP6, but the region of salinification is a lot narrower. Basically, rather than the warmest 6% of the ocean, essentially, getting saltier, you have a smaller fraction, only 2% warmest bits of the ocean that are getting saltier here. And you have a fair amount more freshening as well in the tropics. So we can express these salinity changes that I just showed you before as a freshwater content change. All we do is we take these vectors, which are a ds dt or a dt dt, so delta t and delta s, and multiply it by the volume of ocean that experiences that. Because you might notice there's quite a small amount of salinity change in the subpolar ocean, but this is a huge proportion, 94% of the ocean by volume. So we just multiply these vectors by their volume to get a freshwater content in meters cubed. First, we take a look at the 2% warmest ocean. So that's where the CMIP6 models go from salinifying to freshening. And what we see is that for all of our models, which are in gray, and the 4 observational data sets of interest, we see a net transport of fresh water from the warm parts of the world to the cold parts of the world, right? That's what that means. So that we're losing fresh water in this top 2%, and it's ending up down here because it's a closed system. However, when we look at the 6% warmest ocean, which is where the split occurs in observations, there's a marked difference between CMIP6 models and observations. So observations are all freshening quite a bit. Losing fresh water quite a bit. So basically, a lot of fresh water is moving into the colder regions, subpolar regions. But in fact, the CMIP6 models are having the opposite effect. So a lot of CMIP6 models are actually getting net fresh water into the warm bits of the world at this stage, which is not quite correct. But one of the key results here is not necessarily the difference between CMIP6 and observations, but actually the fact that we get an observational estimate of freshwater transport in our Earth system. So as far as we know, this is the first time someone has quantified how much fresh water moves from the warm bits of the world to the colder bits of the world. It's a critical limb of the water cycle, and we're able to derive that through this water mass-based framework in terms of a volume of water that is transported since 1970. Now, this is, I think I should just stress that this is sort of an Earth system transport. So this isn't necessarily a limb of the water cycle that moves through the atmosphere. It's simply we're seeing the salinification in the ocean and freshening in the ocean. And we're saying through some means, whether that's via an atmospheric conduit, whether that's through currents, or whether that's through another way, fresh water is moving from this warm part of the world to the cold part of the world. So, but it's also really important to note that the CMIP6 models are so off in this respect. And that's something that needs to be dealt with. I'm not showing it here, but some of the work that we did suggests that it has to do with the representation of how surface freshwater fluxes change over time, and that's what's leading to this discrepancy. But watch this space, because that's something that others will hopefully look at. So I'm just going to summarize this bit of work. I will talk about other things after this, but basically what we did was we introduced a novel one-dimensional tracer percentile framework to investigate global heat and freshwater changes. We found that the heat content change for 90% of the ocean by volume occurs through surface fluxes that enter through just 25% of the surface area, predominantly in the northern and southern high latitude, basically subpolar regions. We found that since 1970, 46 to 77 times 10 to the 12 meter cubed of freshwater has been transported poleward, which is sort of the first observational estimate that we know that exists of this. And the CMIP6 suite, 20 different models do not replicate this transport at all. And the closest model underestimates it by 2 to 4 times. So, this is ACEAS, and you guys a lot of you are probably interested in Antarctic science. So I'll just sort of try and tell you a little bit about what my current and future plans are in this space. And, hopefully if some of you have ideas for how you can apply this framework to your specific problem or study, we can chat more about it. But what I've presented here is what we've done so far. We've taken gridded observations in CMIP6 models. We've looked at TNS changes in 1D temperature percentiles, and we've calculated global heat and freshwater budgets. And these are the two references for this work. So hopefully you can search those online and find those. But there's a lot of other things we can do with this methodology. Another thing that we've looked at is we just take a pre-industrial control run of a climate model, ACEAS CM2, and we just assess, we look at how temperature in 1D temperature percentiles and 2D temperature salinity percentiles, so that's that bit I was talking about at the beginning. We look at how the internal variability of OHC changes in this framework. So far, like in this talk, I've just presented on tendencies and long-term trends. We're also sort of interested to see whether this new framework reduces the noise in the system, because it does exclude adiabatic redistribution, as I was saying. So we've done both of these. One of them has been published by Ryan Holmes. That was the 1D temperature percentile framework. And I've got a paper under review looking at the 2D temperature salinity percentile. So this is all work we've been doing in this space. In the near future, we want to use these gridded data sets to look at other tracers. The two big ones are oxygen and carbon dioxide, such that we can try and formulate these O2 or CO2 budgets in the ocean. The real issues we have right now are finding relevant gridded data sets that are not just completely unreliable when it comes to these specific tracers, oxygen and carbon dioxide. But I just want to end with what my plan is when I start at ACEAS in April. What I've shown you so far has been a 1- and 2-dimensional tracer percentile framework applied to the global ocean. It's really nice to apply these frameworks to the global ocean because everything closes. There's no transports in between basins. Whatever you get into the surface is mixed out, so the budgets are quite clean. However, I think there's a lot of scope to explore this problem in the Antarctic margins. And the aim at the moment is to try and do a comprehensive assessment of heat and freshwater fluxes in the Antarctic margins. So just quite briefly, the Antarctic margins are extremely dynamically important because they affect things like sea level and ice melt. And they're also characterized by fluxes of very different types of water masses, all intermingling and mixing with one another and training into one another. So we have a cold and salty bottom water and dense shelf water formation, a warm and salty circumpolar deep water that gets onto the shelf and can trigger melting. And we also have Ekman transporter of cold and fresh Antarctic surface water on and off the shelf. So there's clearly a lot of scope to try and apply these 1D and 2D tracer percentile frameworks to different models. At the moment, the aim is to look at ACEAS OM201 and MOM6, and also to observations. This is where things are a bit more tricky. We can look at gridded obs, 1 degree obs like EN4 and MyMOC. But there are active efforts at the moment to develop new gridded data sets that we can make use of in the future. So that's all I had to present today. So yes, thank you. Thank you very much.
Thank you very much, Taimoor. That was very interesting, very enlightening.
Was mute.
Are there any question, please? Yeah, Jan? No, you're just congratulating, sorry. If you do have a question, you're welcome to unmute yourself and ask the question, because it's hard to
Kathy
see.
has one.
Yeah, here we go, Kathy. Kathy, please.
Oh, thank you for the talk. Great talk. So I was wondering if you could, maybe it's hard to say, but if you could speculate a bit further on what it means when you said that the fresh water is moving from the warm water regions to the cold water regions, and it's either happening via an atmospheric or oceanic route. What is that sort? Could we think of that in terms of maybe there's going to be more rainfall in the cold water regions or more freshening? Is that how you're interpreting that?
Yeah, so I mean, I guess we sort of know that generally, at least in the atmospheric route, you have evaporation in the subtropics, and then that ends up in the tropics and like in the higher latitudes as well. So we know that that limb exists. We also know that that is getting stronger over time. Like basically we have more evaporation and more net precipitation. What we've quantified here is not just the atmospheric limb, basically integrating what's happening in the warm parts of the world and what's happening in the cold parts of the world, but also the effect of currents and other transport processes in the ocean, as well as land-based processes as well. So I guess what this is sort of confirming other studies that, you know, our water cycle is intensifying due to climate change, but it's putting a number on the total transport of fresh water associated with that intensification, not just from the atmospheric route, but also from everything else that goes on in the Earth system that moves fresh water across. Yeah.
Cool. And can you remind me, what was the number roughly, like to order? It
was 46 to 77 times 10 to the 12 meters cubed. I know I need to contextualize that a bit. But
12 meters cubed. Okay,
yeah,
cool.
Yeah.
Thank you.
No problem.
Daniel, please.
Hey, Taimoor, great talk. Thanks so much for presenting it today, and I really appreciated that. So just a quick question. I also sent you a message, but curious about if you have any thoughts on the trend of the freshening being related to possible increase in observation / frequencies in the observed space. So just you had any thoughts on that?
Yeah, that's a great question. And it was because we anticipated sort of a sampling bias that we looked at lots of different observational products. Because like you said, the density of salinity observations has increased a lot since the 2000s, and that can lead to sort of an anomalous trend in salinity just because we have more observations, so we're able to sort of self-correct. And in fact, this is something that you do see in one of the observational data sets, EN4. That's this dashed line over here. You can see that it's chugging along quite nicely, sort of a quasi-linear freshening, and then it suddenly drops to a new normal. And we believe that this is the way that EN4 infills gaps in its observations, and it basically introduces a sampling bias. To try and decrease the impact of that, we used an observational data set that specifically targets these sampling biases that are known to exist by infilling using a model output, CMIP5. And that's the solid and the dashed dotted line, which are matching each other quite well. And so you can see that there's no huge change in the 2000s when the Argo program kicks up. And that's simply because they've used a different infilling method, basically. So we did anticipate that and we did try and account for it. But yeah, that's definitely something to be concerned about. And we don't have an uncertainty estimate here at the moment. But yeah.
Thanks for that, Taimoor. Excellent. That black line, now that you've elucidated that, it really I can see where you are going with that.
Yeah.
Thanks.
Yeah. Thanks.
Thank you, Taimoor. We have another question by Nathan.
Yeah.
Yeah. Thanks, Taimoor. That was a great talk. Enjoyed it very much. A subject close to my heart. So just to contextualize it, I'm thinking of the Paul Durac's paper, right? And so that was an acceleration that was consistent with 7% for 1 degree, a little bit less actually. So in this discussion around the transport and the amount of moisture that's moved, do you have a sense of whether it's like the Clausius-Clapeyron, 2% speed up or 7% speed up in the water cycle?
Yeah, that's a great question, Nathan. So the Durac et al. Paper was sort of our first, was a first look at how the water cycle is intensifying, and they said, yes, 7% per degree Celsius of warming. We can compare our freshwater content change estimates to the surface flux intensification, basically, as a percentage in the CMIP6 models. And we can make estimates for observations, assuming that intensification induces the same response. And what we find is from 1970 to 2014, it's equivalent to around a 7 or 8% intensification of the water cycle, which is higher than the Durac et al. Estimates because that was per degree Celsius. Of course, between 1970 and 2014, we haven't had 1 degree Celsius of warming. So this is estimating higher rates of surface flux intensification in the past than were previously estimated by Durac et al. And we think that's simply because we're taking into account the entire 3-dimensional salinity profile rather than just looking at surface salinity changes, which is what Durac et al. Did.
Yeah. Okay, cool. Thank you very much. And if you want an oxygen gridded data set, I've got one for you.
Oh, great. Okay, let's talk.
Yep.
Thanks.
Zana?
Hi, Taimoor, that was a great talk. Even I was able to understand most of it. But I am curious because I think you mentioned a few times that you assumed that the total amount of water hasn't changed, or the total amount of fresh water. But I mean, there has been, meltwater going into the ocean. So do you see overall, or how does that figure in, and are you able to see that in your analysis?
Yeah, so based on CMIP6 models, we see over 1970 to 2014, we see a 0.03% increase in the total ocean volume. And that's simply because the meltwater input so far has not been that great, but obviously we're approaching tipping points, which will change that formulation quite a bit. And that's something we need to take into account for if we want to do this analysis for future projections. In addition to that, the observations don't have very good estimates of the impact of meltwater on salinity. And you'll notice, if I just go up, actually, this has been cut off a little bit, but you get these crazy changes in salinity right at the coldest bits of the ocean. And that's simply because there's high uncertainty, but also we don't have that meltwater signal very clearly implemented in observations as we do in CMIP6 models. And so basically we avoided that question by just looking at the 6% warmest ocean. because yes, I mean, it's not represented in OBS, and overall in the historical signal, the total volume hasn't changed by all that much yet. Yeah.
Okay, thanks.
No problem.
Sandeep, please.
Yes, Taimoor, it is a good presentation. Yes, I have a small question. You have looked at the global hydrological cycle. In that, you have looked at the precipitations minus evaporations plus the river runoff. So I just have a question, because how much this river runoff is contributing to the ocean freshwater things, global ocean freshwater.
Yeah.
And
yeah, go ahead.
And one more thing is this river runoff, what kind of observation data sets you have taken? Because, river runoff, sometimes that there are a lot of uncertainties are there.
Yeah. So with these P minus E plus R, so you're asking about the R over there.
Yes.
Yeah, so we took okay, I have to remember this. I think, yeah, we took the Dye and Trenberth estimates of river runoff from something like 1,000 rivers or something. I think it's called the 1,000 Rivers data set. And that basically quantifies the river runoff in spur drips for a lot of major river systems. We binned that into 1 degree bins. And what we found was that most of them are pretty negligible in terms of their actual contribution compared to P and E. But the one exception is the Amazon, which will be in the tropical regions and contributes about 1 spur drip of river runoff. So it's still important to implement river runoff in these models because of the influence of the Amazon in the warmest bits of the ocean, because there's not a lot of volume in those tropics, and a lot of that volume input is coming actually from the Amazon runoff. So yes, I hope that answers the question.
Okay, thank you so much.
Yeah, no problem.
Thank you, Taimoor. Yeah, and I would say that doing such an analysis for the oceanic carbon will be quite interesting. So I do agree with your future plan as well. And you might have some gridded data. The GLODAP data, I think, should work. Not sure. Or you take an ocean model.
Yeah. We're just chatting with people right now. We've developed a new data set, so we'll see what happens there. Yeah.
Okay.
Hello, Taimoor. This is Saurabh. I do have a question. And
Yeah,
first of
no
all,
problem.
it's a very nice talk that we already discussed back in Paris. So if we consider Ariane Puric paper about the widespread freshening of the Southern Ocean.
Yeah.
So in that context, and taking your study, is that freshening is mostly from the hydrological cycle or from the melting?
So in the historical period, most of the intensification is through the hydrological cycle. Ariane's work and other pieces of work that have looked at this have implemented meltwaters that are more relevant to longer timescales. So basically what we project will happen with climate change. And in that case, the overall proportion of freshwater fluxes due to meltwater will increase substantially. There is some uncertainty with those works, though, about sort of what the overall impact on the salinity will be, because if your melting occurs at the base of the ice shelves, it'll entrain and mix, and the overall freshwater signal will be diluted somewhat, whereas if you just have it input at the surface, that will change the overall dynamics of the system. But at least in these observational runs, we're not as concerned about the meltwater signal coming from the ice sheets. But this is it's just something that we need to be aware of, because that additional volume flux as well isn't accounted for, which will, as a previous person mentioned, change the total volume of the ocean and make this framework slightly less relevant. So yeah, just something to note for if you want to do future projections.
Yeah, so just curious that like what will be the advantage in that context from your study?
So in that context, looking at projections, I think there is still scope to look at changes in the steric sea level. So basically, the meltwater is going to be contributing a larger and larger proportion to the overall sea level rise in the global ocean. But if we just focus on salinity and temperature changes in the future, then we could potentially constrain steric, so thermosteric and halosteric sea level rise over time. And that's where I see the value in future projections of this work, which is nice because I think that's what you'll be working on, right?
Yeah, so let's chat at the ACEAS workshop more.
Yeah, absolutely.
Yeah, thanks, Taimoor.
No problem.
Okay, well, thanks a lot, Taimoor, and everybody for attending. I think we will finish the discussion here, but that was quite a lively discussion, so thanks a lot. I will also, we're still looking for people to give seminars, so if you want to nominate somebody or nominate yourself, please send us an email. And I guess that's it. I think we'll all see each other in a few weeks in Hobart at the ACEAS workshop. So thank you, everyone. Thank you, Taimoor. Bye.
Thank you. Bye.